Consider the function f of x equals 1,500 times 1.025 raised to the 2x power. First, let's find f prime of x for part A. Well, this 1,500 is going to get multiplied by the derivative of this part. Okay? Quick review of derivative of exponential functions with base that is not e. So something like this. How do you differentiate y equals 5 to the x power? Well, the derivative is going to be natural log of 5 times 5 to the x power. Okay, it's always natural log of that base times the original term, but sometimes you have to use chain rule. Okay, now look at this for me. What if you have y equals 5 raised to the 2x power? Well, it's going to be y prime equals natural log of 5. See, the base is still 5, right? And you multiply by 5 to the 2x power. But you now need to multiply this by the derivative of 2x. Okay, and derivative of 2x is 2. So we have 3 things multiplying here. So let me do one more, and then I'll go back to the original problem, okay? So what if I give you a function that looks like y equals 1.25 raised to the 3x power, okay? Well, the derivative is going to be, you start with natural log of the base, 1.25, and you multiply this by, I'm out of room, let me bring it down. You multiply this by the original term, 1.25 raised to the 3x power. But don't forget to multiply this by the derivative of that exponent. So you will multiply this by 3, okay? So quick review of section 2.6, okay? If you want more examples, I think it was under week 7 overview video that you can find more examples like this. But let's find the derivative of this blue highlighted function, okay? So what do you need? You need natural log of 1.025, right? And then you're multiplying this by the original exponential term, so 1.025 raised to the 2x power. And now, don't forget to multiply this by the derivative of that exponent. So you have to multiply this by what number? 2. So notice all of these are multiplying, so we can try to simplify this, okay? I see there is a number and another number. We can multiply 1,500 by 2 and get 3,000. And we'll just multiply this by natural log of 1.025 and multiply this again by that exponential term. So we found it. Okay, so that's the answer for part A. Okay, now, does the function have horizontal tangent line at any x value? Okay, explain your answer. Now, horizontal tangent happens, we're looking at part B now, when the slope of a tangent line is 0, right? So let's try to find this by setting the derivative equal to 0. Not plugging in x equals 0, but we're setting this derivative that we just found equal to 0. So look, I'll say 0 equals this entire thing, okay? So notice that we got 3 things multiplying, right? Here we have 3,000 times natural log of 1.025 times this term, right? So 3 things multiplying, and we want to see if that can ever be equal to 0. Well, 3,000 will never be 0, right? So like, like typically we would set each factor equal to 0, but that's never going to be 0. 3,000 is not going to become 0, so we don't have to worry about that. Same thing. natural log of 1.025, that is just a number. So if you type that in, it is a number. Is that 0? No, it's not. So the first two multiplication pieces, first two factors I should call, they will never make this entire equation equal to 0. So it all depends on the third guy. Okay, let's see if this guy can ever become 0. Because if the third piece of this product is 0, then whole thing will turn into 0, right? So we'll solve this by setting 1.025 raised to the 2x equals 0, okay? Now, what do we usually do here to bring that exponent down, okay? We would usually take natural log, right? So I will take natural log of 1.025 raised to the 2x power. And then I do the same thing over here, but now we have a problem, okay? Now take a look and see what happens, okay? So over here, I'm going to type in natural log of 0. Okay, let me open up scientific calculator. Desmo Scientific. What is natural log of 0? I'll show you. Undefined, right? So can I take natural log of both sides? I can't, because I can't take natural log of 0. But there's really no other way to bring that down, right? But so now let's think about this, okay? Why wouldn't this work? Can you raise 1.025 to a power, some kind of power exponent, and get a 0 out of it? How many times do you have to multiply 1.025 by itself to get a 0? Never, right? In fact, well, this equation have no solution, because let me see. All right, what can I do? Maybe I can show you a graph of this. Desmo's graphing calculator. I can do 1.025 raised to the 2x power, and I will have a graph like this, okay? So that's the graph. What we're trying to see is when will graph ever hit y equals 0, okay? When will the function value ever be equal to 0? But take a look at this for me, okay? To the right end of this graph, you see the graph is going up like crazy, right? It's never going to hit this blue line y equals 0. Just keep on going. Now it looks like, if you just look at this left tail of it, it looks like it was getting close, okay? It's getting close, 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 but what's actually happening is it is approaching y equals 0, okay? So it actually has a horizontal asymptote of y equals 0, this function does. So it's approaching it, it's getting closer to 0, but it will never actually reach it, okay? So here, we're going to have to say, does the function have horizontal tangent line at x value? We're going to have to say no, because this equation can never be equal to 0. The first one, 3,000, is never going to be 0. This orange number, by the way, if you're wondering like what that number is, let me type that in real quick, okay? If you type in natural log of 1.025, that decimal is like 0.024. It's like pretty close to 0, but that's not 0, right? So the orange one will never be equal to 0. And this green one, we solve from the graph, and also we try to take natural log of both sides. You cannot raise a number, any number, to a certain power and get 0, okay? So because of that reason, okay, hold on. And I'll put this here. None of these will give me 0. So for that reason, we have to say that this function, f does not have horizontal tangent lines at any x value, because f prime can, well, I'll say f prime is never 0. No, I think that's enough. You see what I mean? So if you communicate that, that will be fine. We set the derivative equal to 0. We try to see which one of these can turn into 0 to make the whole thing 0, but we found out that's never going to happen. So That should be enough. If you talk about how the derivative is never equal to 0, therefore does not have any horizontal tangent, that should be good.